Myself, Shaijil J, Department of Mechanical Engineering, Malabar Polytechnic College, Kottakkal, Malappuram. In this session, I am going to discuss on the model question paper of the course Material Science and Metrology. The course code is 3022. Part A, 1 mark question. We have to answer all in one word or sentence. First question, define space lattice. Atoms arrange themselves in distinct pattern in space called a space lattice. Second question, melting point of pure iron is dash degrees Celsius. That is 1539 degrees Celsius. We have to also remember the melting point of metals like copper, aluminium. The melting point of copper is 1085 degrees Celsius and the melting point of aluminium is 660 degrees Celsius. Third question, define phase. A homogeneous portion of system that has uniform physical and chemical characteristics is called a phase. We can also define phase is a physically distinctive form of matter such as solid, liquid, gas or plasma. These are different states we know. It is also called phases. Next question. Machine used for tensile testing is dash. That is universal testing machine. Define span of a measuring instrument. The minimum and the maximum value of a quantity for which an instrument is designed to measure is called its range or span of measuring instrument. Next question. Dash is the ability of the measuring instrument to get the same value in repeated measurements under different conditions. That is called repeatability. Name a mechanical comparator. That is dial indicator. What is meant by mechanical comparator? Simply a comparator. In metrology, the comparator is a precision instrument which is used to compare the dimensions of a given component with the actual working standard. Eighth question. Vernier depth gauge is used for measuring dash. That is, depth of a hole is measured using vernier depth gauge. Ninth question. Clinometer is used for measuring dash. Clinometer is used for measuring angle of slope or elevation. Next, we are going to discuss on part 2B, 3 mark questions. We have to answer 8 questions out of 10. The first question, explain the purpose of alloying in steel. So actually what we are doing in alloying is we are changing the properties of steel. So what are the advantages we are getting or what are the properties we are getting? That is the purpose of alloying in steel. That is strengthening of ferrite. Ferrite means simply it is indicates steel. Second, improve corrosion resistance. So we have different applications, so we have to improve the corrosion resistance. Better hardenability, grain size control, greater strength or to improve the strength, improve machinability, improved high or low temperature stability. So the material has to steel has to work in different temperature. So the ability to work or stable in that particular temperature where it is working. Improved ductility, so improved toughness, better wear resistance. These are the important properties or purpose of alloying. Second question, give the applications of wrought iron. Wrought iron is available in the form of plates, sheets, bar, structural rivets, chains, and a wide range of tubular products, including pipe, tubing, and casing, electrical conduit, etc. So, wrought iron is they have different variety of applications. Nowadays, it is very rare, even though wrought iron has some importance. Wrought iron is are mainly used in building construction, that is underground service lines, electrical conduit. Electrical conduit means some casing for electrical uh, applications. Second, public works like bridge, railing, drainage lines. That means bridge railing means some decorative works or safeguard again on the top of the bridges you can see, or some drainage lines, pipes. Sometimes we are using proteins. Industrial application like condenser tubes, unfed heat exchangers, etc. Railroad and marine applications, diesel exhaust and air brake piping. Gas collection hoods, coal handling equipment, etc. That is the major applications where we are using protein. Here you can see some figures of the applications of protein. These are called as grill works like some. It is when the protein is undergoes some rusting process. It is color changes to brownish, a finished brownish color. That is the beauty of this protein. You can see some the decorative works in the case of some park, etc. Or in the case of old construction buildings, in the old construction buildings, you can see these protein. To resist corrosion, actually, but it is undergoes some aging process. It is a brownish appearance is come, that is a very finished brownish appearance, that is very beautiful to see. You can see in this figure there is a brownish appearance. You can see the color changes. Okay, that is applications of protein. You can just read these paragraphs, so you get some idea about this protein. Third question, briefly explain the classification of cast iron. The classification, that is, the cast iron is, sorry, the cast iron is classified into mainly four groups. First is called the grey cast iron, then it is called white cast iron, third is, there is a ductile cast iron, and last one is called a malleable cast iron. So just we can go through one by one. First one is grey cast iron. Grey cast iron or grey iron has a darker grey fracture color due to a graphitic microstructure. The gray castion, the name itself indicates the color is gray. The carbon present in the castion is two forms. One is in the form of graphite, other is in the form of iron carbide, that is simply called cementite. So in the case of gray castion, it is graphite. Carbon is in the form of graphite. The presence of graphite phase is due to the addition of silicon, which acts to stabilize carbon in the form of graphite as opposite to iron carbide. That means simply indicate the color is gray and it is carbon in the form of graphite. These are different properties like damping capacity is high in the case of gray cast iron. That is peculiarities of the gray cast iron. Second is white cast iron. White cast iron has a white fracture color due to the presence of iron carbide. In the case of white cast iron, the carbon present in the cast iron is in the form of iron carbide or simply cementite that provide a whitish appearance of the cross section or on the fracture area. The presence of carbon in this form are opposed to graphite, that is opposed to graphite. Is a result of lower silicon content compared to gray cast iron. That is, there is a low carbon content. That is why carbon is in the form of cementite. Third one is malleable cast iron. Malleable cast irons are formed by a slow annealing heat treatment of white cast iron. Malleable cast iron exhibit good malleability and a good ductility. That is, the meaning is that malleable cast iron is produced from white cast iron. It is a little bit malleable nature compared to white cast iron. We don't go for comparing with the steel. It is we are comparing with the white cast iron. Fourth one is ductile cast iron. When magnesium or cerium is added to in small quantities to gray cast iron, in a molten condition, leads to a different microstructure on solidification is called ductile cast iron. Not so the spelling mistake, that is cast iron. That means the ductile cast iron is produced from gray cast iron. That is, what we are doing is we are adding magnesium and cerium. Then it is the properties changing. They become ductile in nature. That is ductile cast iron. Presence of graphite in the form of spherical nodules. Hence, ductile cast iron, also known as nodular cast iron or spheroidal graphite cast iron, or simply it is called SG cast iron. So different names you must be remember. That is, ductile cast iron is produced from gray cast iron by adding magnesium and cerium. And this case, ductile cast iron, the graphite is in the form of spherical nodules, and it is called a nodular cast iron or spheroidal graphite iron. So simply it is called SG cast iron. Fourth question: name different failure mechanism in engineering materials. There are a lot of failure mechanisms are there. Here I am going to explain six of them. Six of them. First one is called a fracture. You may heard about the ductile fracture or brittle fracture. That simply means the fracture. When a new crack appear or existing crack are extended, you are basically looking at a fracture mechanism. That is simply called a fracturing. It is maybe brittle fracture, is crack propagation, or it may be ductile fracture. Second is called yielding. When a body experiences stresses, it describes a body which experiences stresses in excess of the yield stress. That is called yielding. Third one is insufficient stiffness, simply called a deflection. When the flexibility causes the failure, the material is flexible. Then when we are applying the load, it will be deflect. That is insufficient. That is simply called deflection. It is called insufficient stiffness or lack of stiffness. Fourth one is buckling. That is generally happen in the case of columns. When a loss of stability creates big damages, that is in the case of columns. That is called buckling. And fifth failure mechanism is by fatigue. Most fatigue failure are caused by cyclic loads significantly below the loads that would result in yielding of the material. That is, fatigue occur due to cyclic loading or variable loading condition. Sixth one is called creep. When a body deforms over time, that is, we are applying a load for a long period of time. So the changes of the material or elongation of the material will be take place due to a great duration under a small load or simply a load. That is called a creep. So there is a matter of time. Creep is occurring the matter of time. Fifth question, explain annealing. Mainly, we are doing the annealing process in the case of steels. That is simply we are softening the material for changing the or to improve the machinability, to relieve internal stresses for different applications. We are doing the annealing operation. So, what is annealing? Steel is annealed to reduce the hardness. So, we are reducing, strength is reducing. The annealing process reducing the hardness or strength. Improve machinability. We are reducing the hardness but improving the machinability. Facilitate cold working. Produce a desired microstructure. So, if you have a stronger work material, that is harder work material, we can make it soften or you can make it undergo some facilitate cold working or to you can use to improve the machinability by doing the annealing on this harder steel material. So full annealing is the process of softening steel by a heating and cooling cycle. We have to heat it and we have to cool it. Such a process, annealing is a particular process, or heat treatment is a particular process. Initially, we have to heat it, then we have to soak it. So that soaking means we have to keep in that particular temperature and again cooling. So cooling determines its microstructure. That means sudden cooling, slow cooling, or intermittent cooling, or very fast cooling, etc. According to that, the property is changing so that it may be bent or cut easily. In annealing, steel is heated above the transformation temperature to form austenite. We are increasing the temperature to austenite state and cooled very slowly, usually in the furnace. In the case of annealing process, in the case of full annealing, we are heating the material to above the upper critical temperature. In the case of hypoeutectured steel, and then it is cooled slowly, soaking for a particular period of time, and then we are cooling slowly. Very slow cooling means we are cooling in the furnace. We are just stopping the furnace, so it will be cooling in the furnace. The slow cooling process. The what are the purpose of doing annealing, including to inducing a completely stable structure, reducing hardness, already mentioned, improving machinability, relieve internal stresses, etc. This is simply a schematic sketch of the annealing process or full annealing. This is a portion of the iron carbon diagram. You can see temperature range and carbon percentage here. And this is the upper critical temperature line. This one and this one. This is called a lower critical temperature line, nearly 723 degrees Celsius. Same for all type of steel. But this will be varying for the composition of the steel. For this particular composition of the steel, this will be the upper critical temperature. For this composition, this will be the upper critical temperature. This is the eutectode point, and so this will be the hyper-eutectode steel, and from this to this side, it is hyper-eutectode steel. So we are heating the material to above the upper critical temperature. That is, this is the austenite range. And then soaking. Soaking means we are holding, and then cooling, furnace cooling will be take place. Sixth question, explain the significance of measurement. We already know what is measurement. Measurement help us to compare unknown quantities with the known quantities. Measurement help us make a quantitative statement about how big, how long, how fast things are. That means we are measuring the size, we are measuring the length, we are measuring the speed, etc. Without measurement, the final product will be full of errors. If you want to manufacture a particular product, the importance of measurement is very important. Some examples are speedometer is used to measure the speed of the vehicle. Measuring tape is used to measure the length of anything, whatever maybe. Define sensitivity and repeatability. These are very, very important terms and we are using in the case of metrology. Sensitivity. The sensitivity denotes the smallest change in the measured variable to which the instrument responds. It is defined as the ratio of the changes in the output of an instrument to change in the value of the quantity to be measured. So, sorry, it indicates how sensitive the equipment, how the smallest change, whatever the smaller change it can be taken or measured, that indicate the sensitivity. Second time is repeatability. Is the closeness of the agreement between the result of successive measurements of the same measure when carried out under the same conditions of measurement. So repeatability means we are taking successive measurements of same or of same item. Then it is indicating the repeated values, same values again and again. That is for repeatability. Next question, explain calibration measurement. A set of operations performed in accordance with a definite procedure that compares the measurement performed by an instrument to those made by a more accurate instrument or a standard for the purpose of detecting and reporting or by adjusting error met in the instrument tested. That is called the calibration. So we are going to test an instrument with some reference instrument or a master. So what are the we are detecting, reporting, adjusting error met in the instrument. That is simply called the calibration. Ninth question, write a note on random errors in measurements. The name indicates random errors that is occurring randomly. This occurs randomly and the specific cases of such errors cannot be determined. But likely sources of this type of errors are small variations in the position of setting standard and workpiece, operator error, etc. Random errors depends on the qualities of the measuring person and the care taken in the measuring process. It is also called as the chance error. It is also called as chance error. In order to minimize the random errors, the measurements are repeated several times and the average, that means we are taking the arithmetic mean, value is taken as the correct value of the measured quantity. So in order to reduce the random errors, we are taking some a lot of readings, or for example, say 3 or 4 readings, and we are taking the arithmetic mean to take the exact value. Or taking some mean value. Explain the importance of force measurement. First one is quality control. That means we are using this force measurement application, importance of force measurement. We are using it for different purposes. One is for quality control, safety, optimization, and lot of other things also. So first one is quality control. For example, force measurement can be used to test the strength and durability of the materials. Quality control, we are to the quality of the material. That means it may be in terms of strength, durability, or other things, such as metals or plastic in case of metals or plastics, and ensure that they are suitable for their intended purpose. So we are constructing or we are manufacturing some particular component, it has to resist some particular force. So the quality in the case of quality control, we have to check it can resist that much force or not. So that is a modern force measurement. We are measuring the force in the case of quality control. Second is safety. By measuring forces, we can ensure that the equipment is used within the safe limits and prevent the accidents from occurring. So we are using a particular component or particular machinery. If the force is exceeding, it may be collapse or it may be some cause some accident. So as part of safety precaution, we have to measure the force acting on that component or the particular machine. Third one is optimization. For example, force measurement can be used to optimize the operation of engines, hydraulic system, and other mechanical system to improve the efficiency or get the optimum efficiency. Fourth one is for research and development. Force measurement is essential in research and development, allowing scientists and engineers to better understand behavior of materials and structures under different laws. Fifth one for sport. In sports also, we can use the force measurement. Is used to in the sport to optimize training, prevent injuries, and improve the performance. For example, force measurement can be measured the impact of forces on athletes during training or competition and identify areas for improvement in technique and equipment. So the force measurement we can also include many other things also. So all the many applications are there in the case of importance of force measurement. Next is part C, 7 mark questions. You have to answer all questions. Each has one or question also. So we have to choose one and we have to answer the best that you can perform. First question, with the help of a neat sketch, explain FCC and BCC crystal structure. The BCC unit cell consists of a net total of 2 atoms. In the case of BCC, net is 2 atoms. You remember. The one in the center and 8 8 from the core. Actually, it is BCC means body-centered cubic crystal structure. It means that in this line there is a slight mistakes. So I'm explaining that is BCC is a body-centered crystal structure. From the figure, I will show the figure. You can understand well. Okay. Body-centered crystal structure. That means a complete atom is inside the body. So you will get one atom, and there in a cube there is 8 corners there, and the eight corner one atom will be there. So each corner atom is shared by 8 other cubes. So 1 by 8 atom is present. So 1 by 8 into 8, you will get the total of one atom plus the body centered atom 1. So total 2 atoms. Net of 2 atoms will be present. In the FCC arrangement, again there are 8 atoms at the corner. Similarly, in the case of BCC, there are also 8 atoms at the corners of the unit cell and one atom centered in each of the face. Each face, there is 6 faces there. Center of each face, there is a 6 atom face also, atoms is there. So it is shared with the another unit cell. So 1 by 2 will be for the one unit cell. So 1 by 2 into 6, 3. So 3 plus 1, that is the total number of the corner atom is 1. So 3 plus 1, 4. Total number of atom is 4 actually. The atom in the face is shared with the adjacent unit cell. Adjacent unit cell what sharing. So it is 1 by 2 will be for particular unit cell. So totally 6 faces. From the figure you can see this is easily. This is FCC. You can see corner atom. This is a cubical structure. Corner atoms 1, 2, 3, 4, 5, 6, 7, and here also 8 atoms is there. And face center atom you can see 1, 2, 3, 4, 5, and 6. In the case of BCC, you can see corner atoms 1, 2, 3, 4, 5, 6, 7, and 8, and the body centered atom is there. So this is completely inside the body. And move to the next question. Draw and briefly explain iron carbon equilibrium diagram. It is iron carbon equilibrium diagram. It is phase diagram is different names like equilibrium diagram, constitution diagram, etc. So you may remember about that. This constitution diagram is also indicate the equilibrium diagram. Also, it is called a phase diagram. Here we have to explain the phase diagram of iron carbon. The phase diagram is a graphical representation of different phases of a substance that exist within a given temperature, pressure, or weight percentage. So, in the case of equilibrium diagram or ion carbon diagram, we are taking pressure as a constant. So, variables are temperature and the composition, that means fraction of weight or mass fraction or whatever maybe we are taking. Understanding ion carbide phase diagram is important in the fields of metallurgy and material science as it helps predict the microstructure and properties of steel and other ion-based alloys. That is simply indicate the importance of ion carbon diagram. This ion carbon diagram is also called the ion carbide diagram. The ion carbide phase diagram is commonly utilized to comprehend the various phases present in the steel and cast iron. So in the phase diagram, we can identify what are the different phases present in these cases, which are composed of iron and carbon along with the minor quantities of other elements. The iron carbon diagram depicts the relationship between iron and carbon across various temperatures, compositions, and iron phases. Although iron carbide is considered as metastable phase, the diagram can be regarded as representing the equilibrium transformation during slow heating and cooling process. That means the iron carbon diagram indicates the equilibrium passing through the equilibrium states only. So each phases are under an equilibrium condition. That is a simple the meaning of this. The iron carbide phase diagram is a graphical representation of how iron behaves at increasing temperatures on the y-axis and increasing percent of carbon on the x-axis. That means temperature is taking on the y-axis and the percent of carbon or iron is taking on the x-axis. Initially, at the 0 to 0.008% of carbon, that is negligible amount of carbon, make it an impurity and not an alloy. That is, we are at the 0.008 is nearly we are considered zero. That is why we are taking it is not an alloy, we are taking it as an impurity in the iron. Iron acts as a pure substance. Iron is pure and the carbon is impure. In this range only. Other case we are taking as an alloy. This is for just understanding purpose only. Don't be confused on this. As the percentage of carbon increases, it starts forming an alloy with the carbon until it reaches the solubility limit. So that means it is as per the solubility limit, it is forming the different phases based upon the solubility limits are there for particular temperature and for the percentage of carbon. This is iron carbon equilibrium diagram. You can see this is a temperature range. You can see the y-axis. This is the composition. Here you can see up to 2.14% of carbon we are considered this is taken as steel and above 2.14% we are taking it as cast iron. So but it is we are not taking for cast iron much more up to 6.7 it is maximum range, but we are not in the case of application we are not taking up to this range. We are taking around this range only. 4.30 or that range we are taking the cast iron. In the case of casting purpose, we are rarely moved to we are beyond 6. So here you can see the iron carbon diagram. It is also called iron carbide diagram. Why? Because you can see the carbon percentage here are decreasing the carbon percentage. When it becomes 6.7, at this range it is entirely it becomes immediate or simply iron carbide. Simply it become iron carbide. So we can say that it is starting from the iron is 100% iron is here, but it is become simply it is 100% of iron carbon at this point at the 6.7% of carbon. So that is why it is called as iron carbide phase diagram, or we can say it is iron carbon diagram because beyond this we are not required. That is Beyond this, there is no matter. There is no need because it is simply iron carbide only. So here we got to identify. You have to remember the temperature range, percentage of carbon, different phases, and what are the reactions. The microstructure is not required, but if possible, you have to remember what is changes in the microstructure. This is the liquid region that is at 1539. Actually, it is 39, it is 38 degree. Don't confuse 39, 38 or 40. It is the melting point of the iron simply. So above this, we can see that this is a 0.008% of carbon. This is melting point is 1539 degrees Celsius. So the carbon increasing, the melting point is decreasing. Anyway, this is a liquid region in the case of iron carbon diagram. So undergoing cooling, you can see this point is called a delta ion or delta ferrite. This is called a gamma ion or it is simply called austenite. And this region, you can see this called this small region near to the y-axis, a small region you can see that is called alpha ferrite. Alpha ferrite. And here it is delta. This is liquid region, so this become delta plus liquid region. This is delta and this is austenite. So this small region become delta plus austenite region. So and this point is called the peritectic point. Peritectic that is a solid liquid under a cooling process it become a solid. Under solid that is peritectic point. This is austenite gamma ion. So this is liquid. This become gamma plus liquid austenite plus liquid region. And this point is called solid is transformed into two other solid. So this point is called eutectoid point. Eutectoid. Austenite simply undergoes cooling process at this 0.8%, 0.76% of carbon range, and the temperature is 727 degrees Celsius. Sorry. Eutectode reaction will be occur. So the austenite is simply moves changes to ferrite and cimenite. So this is simply called pallite. This is called production is this is called pallite. You can see this is a palladic structure here actually. The figure is here. This is a palladic structure. You can see alternate layers of ferrite and the cimenite you can see. So this is called pallite. This is austenite. That is this is indicating austenite and undergoes this different points. What happens? Here this line that is this point is austenite and this is changes to ferrite and pallite region. The ferrite is more here. This is you can see pallite. This is ferrite. White region is ferrite and these alternate layers indicate the pallite. So when we go beyond this 0.76 range, it become the cimenate is going on increasing. You can see here this is cimenate formation. You can see this when cooled austenite to this region that is to the right of this 0.88 percentage of carbon. Cimenate is forming. On left you can see this is ferrite is forming. So when it is crosses 727 degrees Celsius line, you can see this dark region is called cimenite. Alternative layer of pallite is there. So when it's moving this direction, pallite is goes on decreasing and cimenite is goes on increasing. So that is simply indicating. This is called a eutectic point. That is liquid state of iron and carbon. That is liquid molten state. It is undergoes cooling at this temperature. That is 1147 degrees Celsius undergoes cooling at this point 4.3% of carbon. It is called a eutectic point. So this is producing Lidabrit. That is, labrate is combination of austenite and iron carbide. Perlite is combination of alpha ferrite and this perlite. Here, sorry, alpha ferrite and cementite. That is called simply perlite. Here it is gamma iron അല്ലെങ്കിൽ gamma ferrite or gamma iron plus iron carbide Fe3C or cementite is simply called didaberate. You can see didaberate. So when goes on in this direction, it is a common, you will get didaberate plus cementite. In this direction, austenite plus and didaberate. You will get austenite and didaberate like that. So just I understand what are the different points, what are the temperature. I can see this is 1538 or 39. This is for 93. This is 1000, 1493. This is 1394. This is 1147. This point is very important. 9. This is 727 degrees Celsius. This is called the lower critical temperature line. This is actually the upper critical temperature line for hypo eutectode steel, and this is upper critical temperature line for the hypo eutectode steel. Okay, just go through this. Only you know this thing, I think. This is simplified diagram, so you have to in the textbook or maybe you guys will see. So different points are easily you can understand, but there is no microstructure is given in this figure. Peritectic point, eutectic point, and eutectode point. Here it is simply indicating the reaction alpha plus Fe3C. This is perlite is forming. Gamma undergoes cooling. This perlite is forming. Here liquid undergoes cooling. You are getting lidabrate gamma plus Fe3C. So remember this. Study this well. This is important in the case of heat treatment process, what are the study of steel, etc. So these are different structure you can see. This is the portion of the end carbon diagram. This is upper critical temperature line. This is upper critical temperature line for hyper. This is for hypo. This is lower critical temperature line. That is why it is U1, upper critical U1. This is also upper critical. This is lower critical L1. You can see. So you can see the structure. Austenite is here. When goes through this region, it is forming some ferrite. You can see here it become perlite and some ferrite. In this region again austenite. Here it is cementite is forming. Didabrites you can see again it is become perlite at this region it become perlite. So cementite is increasing, perlite is decreasing when it is moving in this direction. Didabrite is in this region. Third question, explain the procedure for performing the Brinell harness test. Already you have done, all of you have done the test on the material testing lab. So some important points I have to mention. Consisting of pressing a hardened steel board or tungsten carbide board or steel board into a test specimen. The size of board is 10 mm diameter. Board is used for the purpose. That is this ball 10 mm diameter. Your hardened steel ball is used for this purpose. What is the hardness test? Specimen is placed on the anvil. The hand wheel is rotated so that the specimen along with the anvil moves up and contact with the ball. The specimen is placed on the anvil and we are moving the anvil upward direction. The ball is fixed on a particular point. So it will be undergo some impregnation on the material. The desired load is applied mechanically or hydraulically and the ball pressed into the specimen. So when we are lifting the specimen, it will be applying some force on the ball and some impregnation will be done on this specimen. The diameter of the indentation, that is impregnation means the indentation is formed. The diameter of the indentation made in the specimen by the pressed ball is measured by the use of a microscope. So when the ball is pressing the specimen, there will be an indentation. So diameter will be less than the diameter of the ball. So that is diameter of the ball. Indentation is D capital D. That is size is 10 mm. That is 1 centimeter. The indentation is less than that. So that means less than 10 mm. We measure this indentation using a micrometer microscope. The indentation diameter is measured at the at two places at right angles to each other, and the average of these two readings are taken. So we are taking two readings at right angles, and average of this taken as the diameter of the indentation. From the indentation, Bernal hardness number or Bernal hardness value BHN Bernal hardness number is calculated, and the hardness of the particular specimen can be found. So from that BHN value indicate the hardness value. So this is a test apparatus. This is the anvil. On this surface of the anvil, we are placing the sample or the specimen. The ball is placed on this particular ball holder. You can see when we are lifting the specimen with the anvil. So this is the diameter of the ball 10 mm, and it will be some producing some indentation that is less than 10 mm. So that is small d. From this we can calculate the Brenner hardness number. Brenner hardness number actually it is not a BHN value. BHN value, we are indicating BHN value. It is simply mistaken. Right? Is the load divided by the surface area of the indentation. Load by surface area of indentation. That is actually the Brenner hardness number. Diameter of the impression is measured with a microscope with a superimposed scale. The Bernal Arts number is computed from the equation. HP, it is also indicated like HP or BHN value. BHN is equal to 2p by pi d into d minus root of d square minus d square. The P is a load, applied load. P is indicating applied load in the kilogram force, and the pi d is the actual diameter of the indenter, and small d is the diameter of indentation. This HP is also indicating the Reynolds number, I think. So sometimes generally we are saying BHN value, the Reynolds number. Okay. Can move to the next question. Fourth question: explain magnetic particle inspection test. This method of non-destructive testing acts as a supplement to radiography because radiography ordinarily cannot detect the small cracks, especially when they are too small to be seen with the human eye. This is a small indication of this test setup. You can see this is a workpiece. You can see simply it is a component. Maybe it is a cast product or what, or maybe it has some cracks somewhere. There is a crack is there. So we are applying some magnetic field. It will be North Pole and South Pole. So in the crack region, you can see we are also using some magnetic particle. So in this crack region, it is there is some crack is of this two sides will be again act as south and north pole. You can see it is south, this become north, this become north, and this become south. So both will be attracted. South and north will be attracted. So particle will be accumulated in the region where it is crack or defect is present. So that is actually happens. When a piece of metal is placed in the magnetic field and the lines of magnetic flux get intersected by the discontinuity. Discontinuity means a crack, such as a crack or slag intrusion in a casting. Magnetic poles are induced on either side of the discontinuity. I already mentioned to you with refer to the figure. Discontinuity causes an abrupt change in the path of magnetic flux flowing to the casting normal to the discontinuity, resulting in a local flux leakage field and interference with the magnetic lines of force. This local flux disturbance can be detected by its effect upon magnetic particles which collect on the region of discontinuity. So this magnetic particle will be collected the discontinuity, so we can identify where the point of defect is occurred and pile up and bridge our discontinuity. So this magnetic particle will be pile up on the defect point, and the bridge will be bridge like formation, that is pile up will be take place, piling of the magnetic particle. A surface crack is indicated by a line of fine particles following the crack outline, and a subsurface defect by a fuzzy collection of the magnetic particles on the surface near the discontinuity. This is a magnetic particle inspection test. Fifth question, explain the case hardening process, nitrating and cyanide. So why we are doing case hardening? So whenever we require a hard surface and a soft core, we are doing the case hardening process. So many types of case hardening process are there, like carburizing, nitrating, cyaniding, etc. In this question, we have to study about the explain about the nitrating and cyaniding. Case hardening or surface hardening is a process of hardening the surface of metal object while allowing the metal deeper underneath to remain the same, thus forming a thin layer of harder metal at the surface. The top surface of the metal or the compound is harder, and inside is soft. The core is soft. So where we are using, for example, you can see here some shaft, some gear, etc. In the case of shaft, it is rotating inside the bearing or inside the housing. So wear and tear is more in this surface. So when it is making more hard surface, we are making hard surface by using maybe in the case of nitrating or carburizing or cyaniding. So the wear resistance will be increased or improved. So that is a process of doing the case hard. The case of gear teeth, it is meshing with some other teeth. So that wear and tear is more. So it should be make harder. So the wear and tear will be less. So, sorry, internal core will be soft in the case of gear. So the hard surface and soft core, that is the application or that's the purpose of doing case hardening. I'm skipping carburizing, that is not mentioned in the case of sorry, this question. The working is of the case of the carburizing, nitrating, sanding are same. This is a container. You assume there is a container. It inside this material, inside this box, we can place the component, and surround this component, we are placing the material. If it is carburizing, we are providing carbonaceous material. For example, it is activated charcoal. If we are doing nitrating, we can use ammonia. If cyaniding, we are using some other material for that for that purpose. Okay, one by one we can move. So that is and heating the material, heating inside this, so the carbon will be attracted or diffused in this surface of the material. So depth is controlled by the temperature, the time, etc. We are heating the container, so the heated condition. So carbon will be diffusing into the component surface. So that is a carburizing process. Similarly nitrating is take place. In the case of nitrating, nitrogen is entering into the component, diffused into the component surface. In the case of cyaniding, sodium cyanide we are using, and the nitrogen and carbon is diffusing into the surface of the material. So carbon is increasing hardness, nitrate is increasing the hardness. Carbon and nitrate, in the case of cyaniding process, is increasing the hardness of the surface. So this is nitrating. What is nitrating process? The components to be nitrate are placed in a heat-resistant metal container which is filled with ammonia. When it is completely purged, it is sealed, placed in a furnace and raised to a temperature of approximately 500 degrees Celsius. At this temperature, ammonia dissociate and form nitrate. The formed nitrate is then absorbed in the surface layer of the steel. Parts are maintained at 500 degrees Celsius for between 40 to 100 hours, depending upon the depth of case required. I told you, already mentioned, what is the depth. According to that, the time is controlled. After which the parts are allowed to cool in the container. That is called a nitriding. So simply a schematic figure of a nitriding process. The compound is here. It's a ammonia. It is a container. It is heating. So nitrogen is entering into the surface, diffusing into the surface. Next one, cyanide. The cyanide, carbon and nitrogen are introduced into the surface of the steel. Now, here we are introducing carbon and nitrogen. Nitrogen, only nitride is entering. Here, carbon and nitrogen is entering. By heating it in suitable temperature and holding it in a contact with the molten cyanide to form thin skin or case which is subsequently quench hardened. Negligible dimension change is caused by cyaniding. So we are adding the carbon and nitrogen into the surface. Dimension change is negligible. This quench hardened means after cyaniding we are quenching the component, that is quench hardened. Simply the schematic figure of cyanide. This is a component or workpiece, the tank. Generally we are using sodium cyanide for the cyaniding process. Cyaniding is mainly used on low carbon steel. The part is heated 870 to 950 degrees Celsius in a bath of sodium cyanide, and then it is conjured and rinsed in water or oil to remove any residual cyanide. The process produces a thin, hard shell, 0.5 to 0.75 mm, that is harder than one produced by carburizing. So the cyaniding is more harder than carburizing and can be completed in 20 to 30 minutes compared to several hours. It is typically used on small parts. Cyaniding is mainly used in small parts. The major drawback of cyaniding is that cyanide salts are poisonous. Cyanide it is poisonous. That is very dangerous part of this cyaniding. This time is less comparatively to the carburizing process and can be completed in 20 to 30 minutes compared to several hours of carburizing. Sixth question, sketch and explain ask numbering. It is also called isothermal quenching. Actually, a question is up to this sketch and explain ask numbering. So you remember isothermal quenching is also means ask numbering. What is the purpose of ask numbering? To produce lower bayanite in high carbon steel, 0.5 to 1.2% carbon steel, that is high carbon steel, and low alloy steel, to avoid residual stress generated during quenching, to avoid distortion and cracking. So when we are hardening the steel, we are doing the quenching. So distortion and cracking will be occur. So after the quenching process, we are doing tempering. So the net effect is quenching, then tempering. So in the case of tempering, it is an interrupted quenching process. Isothermal quenching, or it is also called interrupted quenching process. So we are get a little bit softened material, not very soft. It is hard, and that is the condition is called the bayonetic condition. Bayonet, where the material is called bayonet. That is not present in the iron carbon diagram. So it is an interrupted quenching process. Range of temperature used. Austenitized steel is considered. We are taking the austenitized steel. We are increasing the temperature of austenitized stage. Then we are quenching in a particular manner. Quenched above MS, that is martensite, MS indicating martensite start formation. That is quenching, we will get martensite. So martensite is formation starts at some particular temperature, that is nearly 250 degrees Celsius. That is MS. From the figure, you can identify what is MS. For the homogenization of the temperature across the sample, then instead of quenching the sample, it is held at this temperature for it to transform to a bayonet. In this case, we are initially they quenching the austenized state material steel into a particular range. Quench, suddenly quench, not to room temperature, to a particular range. Then keep at that temperature, that is called isothermal. Keep that temperature for some transformation. Then it become binite, then it is quenching. Some do not require to be tempered. In the case of hardening process, we are quenching and we are temper. But in this case, in the case of ice tempering, post tempering process, there is no need for tempering. We get a tempered material, simply it is called a binite. So here you can see the figure of post tempering process. This is actually it is from a TTT diagram. I think you don't know, you don't confuse. This is a this is from time temperature transformation diagram. It is called a C curve. Simply it is called a C curve. You can see two lines. This is twilight start, twilight finishing process. Okay. Anyway, you don't confuse about this part. Simply you assume this is a stable region. This is a dotted line above that. It is a stable range of oscillate. You assume it is from the iron carbon diagram. What is oscillate? That is the oscillate we are taking in this range. So oscillate is at the formation is you can see it is gamma ion. Oscillate is equal to gamma ion in a particular temperature range. So we are suddenly cooling to a particular range of temperature. This up to this range. This is martensite. Martensite is the hardest form of the steel. Start temperature and martensite finish temperature. Start and finish of martensite. That means if you take austenite in the iron carbon diagram, austenitic range that is gamma ion, that is stable condition. If you suddenly cooling with the water or quenching in a water, you will get martensite. On cooling, you will get martensite. But in this case, austenite you are cooling up to this region only. That is on 215 degrees Celsius, martensite start forming. This temperature is 215, 215. But above that temperature, there is temperature range is nearly 540 degrees Celsius, nearly 540 something degrees Celsius. This region is nearly 540 degrees Celsius. So just above the 215 Martin start temperature range, you are just up to that point you are just quenching, and then keeping at that temperature. For example, I am saying this 260 degrees Celsius. You quench it to 260 degrees Celsius and keeping at this temperature 260 degrees temperature for a long period of time. What happened is the transformation will be take place. Your transformation take place and it become finite and undergo. Then it is after the transformation you are cooling slowly. You can see temperature is decreasing with respect to time. Here the temperature is constant with respect to time, this region. So that is isothermal transformation, simply called Austen process. Sorry. After Austen you the product we got is bayanite. This is stable Austen, this is unstable case. This is another figure of heat treatment. This is actually we are taking a material, increasing temperature to our state range, above that is 91 degrees Celsius. Last figure I explained from this region, pasteurized region to this bariatric region, that is cool to room temperature region. So initially we have to, for heat treatment, initially we have to heat the material at the austenite range, then sudden quenching. At nearly here you can see the temperature range is 360 degrees Celsius. Last case I told you 260. You take this 360 degrees Celsius and keep at that temperature. The transformation will be finished. Then your the austenite formation is completed and slow cooling to a room temperature. That is called the Austen tempering process. So remember the product is bayanite. You got the bayanitic structure. Seventh question: explain primary and secondary standards of measurement. Primary standard: they are material standard under most careful condition. They are not used for directly for measurements but are used once in 10 or 20 years for calibrating secondary standards. Primary standards are maintained at the national standards laboratories in different countries. The primary standards are not available for use outside the national laboratory. These primary standards are absolute standards of high accuracy that can be used as ultimate reference standard. That is used as a reference standard. Next is secondary standards. The value of the secondary standard quantity is less accurate than primary standards. It is obtained by comparing with the primary standard. These are also copies of primary standards with respect to design, material, and length. This also acts as safeguard against the loss or destruction of primary standard. Next question. Write short note on systematic and random errors in measurement. Systematic error. Systematic errors are due to some known causes according to a definite law and are tend to be in one direction, either positive or negative. We can minimize the systematic errors by selecting better instruments, by improving the experimental techniques or produce or procedures, and by removing personal errors as far as possible. There are four sources or types of systematic error. One is instrumental error, second is gross error, third is error due to external causes, fourth one is error due to imperfections in experimental procedure. So first one, instrumental error are errors due to the apparatus or measuring instruments used. Second is gross error. The gross error is another type of systematic error which are committed due to the personal peculiarities of the experiment like carelessness. Third one, error due to external causes. These errors arise due to change of external conditions like temperature, wind, velocity, etc. Error due to imperfection in the experimental procedure. Some errors occur due to imperfections in the experimental arrangement. Next is random error. These occur randomly and the specific causes of such errors cannot be determined. But likely sources of this type of errors are small variations in the positions of setting standard and workpiece, operators, error, etc. Random errors depends on the qualities of the measuring person and the care taken in the measuring process. It is also called as the chance error. In order to minimize the random errors, the measurements are repeated several times and the average, that is arithmetic mean value, is taken as the correct value of the measured quantity. Write a note on the classification of comparators and their characteristics. The comparator is an instrument used for comparing the dimensions of a component with a standard of length. It is a precision instrument which is used to compare the dimensions of a given component with the actual working standard. The purpose of comparator is to detect and display the small difference between the unknown linear dimensions and length of standard. Difference in length is detected as a displacement of sensing probe. The important and essential function of the instrument is to magnify or amplify the small input displacement so that it is displaced on an analog scale. The characteristic of good comparator, that is some important characteristics of the comparators are display or indicating system should be display certain least possible. Least possible display must be a or display a result in least possible time. Sensing or contact point should be hard enough to minimize the wear effect. Wear and tear is minimized. We have to minimize that is another property. It must have a high magnification in order to measure or detect very small change in input. It should be free from backlash and unwanted friction. So it is free from the backlash that will give the correct value or unwanted friction. Also, if there is a backlash is there, the value will be changing. When unwanted friction is there, the value is changing. So there is some applications are there. Generally, this is some general about general things about the comparators. Check the parts in mass production at a very fast rate. You have to check the components in very fast rate. We are using comparators. In fact, newly purchased gauges, um, they are worked as a laboratory standards, or it is a selective assembly of parts. It is used in there are some applications. Actually, we have to deal with the classification of the comparators. There are five classifications you can see. That is mechanical comparator, mechanical optical comparator, electrical and electronic comparator, pneumatic comparator, and optical comparator. This is based upon the techniques or the classification is based on the technique. For example, mechanical comparator works on gear and pinion. Pneumatic comparator using high pressure air. Optical comparator works on using lens, mirror, light source, etc. Electric comparator works on using setup or step down or step up transformers. For example, electronic comparators working using amplifier, digital signal, etc. So comparator is also there. So using any combination of any two things you already mentioned, that is a combined comparator. So what are some examples of mechanical comparator? That is dial indicator, read type comparator, sigma comparator. For optical comparator, you can see Cook optical comparator, the SIS ultra optimeter, the opti gauge. In case of electrical comparator, you can see electrical check, electric check, electricator, electric gauge. In the case of pneumatic comparator, you can see Solex pneumatic comparator. 10th question, explain the principle of working of an autocollimator. An autocollimator is a precise optical instrument used for measuring small angular deviations or tilts of an object's surface or the alignment of optical component. So we can find out the angular deviations or angular tilt of the component we can identify. It operates based on the principle of reflection and the measurement of the angle between the two incident and reflected light beams. How the autocollimator is working. Before that, you must know the different parts of this. There is a focal plane is there where we are getting uh, taking the dimensions from the final calculation. The eyepiece is there, the viewpoint is there. You can see there's a collimating lens is there. Collimating lens is here. There's a beam filter is there. There's a light source that is a lamp is using. There's a diffuser. So light after striking the light source, it is passing the objective lens and then it is striking on the reflector. Reflector is actually the workpiece or specimen. You can see. So we can find the value using some equations. For an equation to find the angle is PQ is equal to F theta. Theta is the angle of reflection we have to calculate. So that we are finding out from this the distance we got the distance between these reflector rays we are taking here. So that distance is PQ and that is equal to F theta. From that you can find out the angle of inclination theta. Okay, we can just explain what is the things happening in this working of the autocollimator. The light source is used to generate light rays so that it reaches the reflector. Reflecting surface is a surface that serves as a workpiece for the autocollimator. The angle of tilt is of this reflecting surface is to be measured using the autocollimator. Diverging lens, also known as the objective lens. This is the objective lens. So light source is coming. It is a beam splitter. It is splitting, and is you can see it is moving this direction, striking on this, passing through the objective and reflecting and strike on the reflector. That is actually the workpiece simply. And after that, the reflecting rays, you can see this angle is 2 theta. This parallel. You can see this parallel. This coming back and try striking on the collimating lens, and it is back to this focal plane. The diverging lens, also known as the objective lens, is used to paralyze the light rays that come through the beam splitter so that they reach the reflector in parallel. The beam splitter is used to split the light rays and direct it towards the objective lens. The light rays that have been reflected reach this target gratic- graticule, and the distance between the incident and the reflected rays is traced in this target graticule. It is used to clearly see the incident and reflected ray point in the target graticule and measure the distance between them. From that distance, we can find out the angle theta. That is, the distance is PQ. PQ is equal to 2 of theta. From this equation, we can calculate the angle theta. 11th question. Describe measurement using angle gauge. Angle measurement using angle gauge involves determining the angle formed between two lines of surface accurately. Angle gauges are tools designed for this purpose and come in various forms including protractor, bevel gauge, and digital angle finders. Choose the angle gauge. Select the appropriate angle gauge for the specific application. Prepare the surfaces. Ensure that the surfaces or lines between which we want to measure the angle are clean and free from any obstructions or irregularities that could affect the accuracy of the measurement. Position the angle gauge. Place the angle gauge on the surface or lines whose angle we want to measure. Align the gauge so that it sits flush against the surfaces, ensuring a secure and a stable contact. Then read the measurement. Depending on the type of angle gauge, we will either directly read the measurement from the gauge or take a reading from the scale or digital display. The last step is to record the measurement. Once we have obtained the measurement, record it for reference. The last question, explain the importance of machine tool testing and list the various tests conducted. The major tests that conducted on machine tools are testing the quality of slide, that is, testing the quality of slide widths and the locating surfaces, testing the accuracy of the main spindle and its alignment with respect to other parts of the machine tool, testing the accuracy of the parts produced by the machine tool. So simply, what is this question indicate? This is an analyzed question. Uh, Importance of machine tool testing. Machine tools means it may be a lathe, it may be a drilling machine, it may be a milling machine. So what is the importance of testing this lathe or drilling machine or milling machine, etc.? This is the various testing. What are the different various tests conducted? So in lathe, we are performing some operation. In drilling machine, we are performing some operation. In case of milling machine, we are performing some operation. So for the performance of this operation, the quality of this operation quality of the components which is coming out of these operations or from the machine tool depends upon the lot of characteristic like alignment of the machine, the surface finish of this equipment, guide ways, ride ways, performance of the equipment, what is the operation, what is the performance, whether it is in the correct quality level or not. These are the things we have to take into account. So we are conducting various tests for different parts of the machine tools. So some of them are parallelism. So sometimes for example, if it is a gateways, the movement should be parallel to the particular point. So the parallelism must be ensured. Straightness, for if you, for example, lathe, if the carriage is sliding over the bed, so there must be straight or surface finish is very important. So the smooth movement. Crossroad is there, and there is a center point of the live center is there, that center is there. Both will be comes in single point. So straightness must be very important. Coaxial, if a drilling, the operation is conducted. Coaxial is very important. Roundness, run out, alignments, these are very important. Test we are conducted in the case of machine tools. Last one is very very important is surface finish. Surface finish is very important in the case of machine tool. In the case of the operation performed, it is in the case of the alignment of the equipment, whatever may be, it is very important. So these are the some tests we are conducted in the case of machine tools. So on this point, you can explain by taking different machine tools. We can explain what are the different checks we are carried out. So now it's over. The question paper is over. We discussed all the questions, including 1 mark question, 3 mark question, and 7 mark question. Okay, thank you.